Hey everybody, it's Jared Pistol doing a video for Simpson Math at Temple College. Today we're turning in a major assignment, and as part of the assignment I had to choose one of the problems from the assignment to explain and solve over this video. The problem I went with was number 3, which is 12x to the 4th plus 53x cubed plus 66x squared plus 12x minus 8. And we're going to solve this by using the possible rational root theorem and synthetic division. The first step is to list all possible rational roots. And how we do that is we're going to take the factors of the constant and divide them by the factors of the leading coefficient. And I'm going to show you what I mean. The constant in this equation is going to be 8 because 8 has no x value next to it. And the leading coefficient in this equation is going to be 12 because 12 has the x value with the highest exponent. And so as a result, 12 is going to be the leading coefficient. So our factors of 8 are going to be 1, 2, 4, and 8. And we're going to write them down like we would possible numerators in a fraction. And then we're going to take that dividing line, and then we're going to write down all the factors of 12, which is 1, 2, 3, 4, 6, and 12. And this is the way that you write all of them, but the way that we need to understand them so that we can do letter B is any of these number combinations, a number on top plus a number on bottom, any of these could be a possible rational root. Not to mention, they could either be positive or they could be negative. We need to make sure that that's a possibility. So all of the possible rational roots, if I wrote them out, would be 1, 2, 4, 8, 1/2, 1/3, 1/4, 1/6, 1/12, 2/3, 4/3, 8/12, 8/3, -1, -2, -4, -8, -1/2, -1/3, -1/4, -1/6, -1/12, -2/3, -4/3, -8/12, and -8/3. And I know some of you may be watching this video and are probably thinking right now, there's a couple of fractions, possible rational roots that he didn't mention. Like I didn't put in 4/6. Well, I didn't need to, because 4/6 is equivalent to 2/3. And if it doesn't work with 2/3, it's not going to work with 4/6. So you don't need to worry about writing fractions that are equivalent to one another over again. For instance, you can write 1/2. You don't have to write 2/4 because that's the same thing as 1/2. And so you don't need to worry about that. The next step is to use synthetic division to test the possible rational roots and to find an actual root. And we're actually going to repeat this process twice because we started out with an exponent of 4. We need to get the leading coefficient down to an exponent of 2. So we actually need to synthetically divide. We need to go through the process of synthetic division twice so that we end up with a quadratic formula, because that's a lot easier to factor. And so first we're going to start off with, here's getting ahead of myself. Here's how you synthetically divide. You're going to take the numbers in the equation. You're going to leave out the x values, but you're just going to list them down. So first we have 12, 53, 66, 12, and 8, just like they are in order in the equation. Then what we're going to do is we're going to take one of the possible rational roots, and we're going to use synthetic division. So let's just use 1, because that's the first one that comes up, is 1 over 1, which is 1. And we're going to put that on the outside of this synthetic division. So the first thing you're going to do when you synthetically divide is you're going to take the first number and you're always going to bring it down below the synthetic division line. And then what you're going to do is any number that is below this line, you're going to multiply by whatever number you're synthetically dividing by. So you're going to take 12, multiply it by 1, you get 12. Well, once you're done multiplying the number on the bottom and the number that you're synthetically dividing with, you add it to the bottom line again. So with the first one, you just brought it down. The next one, you're taking this number times this number, and you're bringing it to use in an addition form with the next number. So we have 1 times 12 is 12. The 12 goes here. So we add 12 to 53, and we get 65. So 65 is back on the bottom again. We're going to take the 1, multiply it by the 65, which is 65, and we're going to put that right below the 66. Add the two together, 131. 131 times 1 is 131. Add that to 12, you get 143 times 1, 143. add 143 to negative 8, and you get 135. So and I'm going to show you, so we have our answer, although the answer tells us that 1 is not a possible rational root. And you know that it's not a possible rational root because this number is 135. What the number should be is 0. So whenever you whenever you synthetically divide by one of the possible rational roots and you get a 0 in this corner right here, when that constant oh boy, what's the word? It cancels out. When the constant cancels out and it turns into a 0 here on the bottom, that is a rational root. That's what's called an actual root. So that is what you can actually divide it by. So I've done this question ahead of time for the sake of the video, and as a result, I know that negative 2 is going to cancel out that constant. So when you see here, we're going to use synthetic division. You bring down the 12, because you always bring the first number down. Multiplied by negative 2, you get negative 24. Add negative 24 to 53, you get 29. Multiply by negative 2, you get 58. Add that to you get negative 58. Add that to 66, you get 8. Multiply that by negative 2, you get negative 16. Add that to 12, you get negative 4. Multiply that to negative 2, you get 8. Add that to negative 8, you get 0. So it cancels out. And so what you're doing is, so we found the actual root, which is negative 2. Now, to put this in a different way, what we're essentially doing is we are taking the equation 12x to the fourth plus 53x cubed plus 66x squared plus 12x minus 8. We're taking the original equation here, and we are dividing it by x plus 2. So when you divide it by x plus 2, so x plus 2, when you make x plus 2 equivalent to 0, and you solve for x, you get negative 2. And that's why we have x plus 2 here, and that's why we have the negative 2 there, because the signs change when you solve for x. But essentially, this whole thing right here, this synthetic division, is the same thing as writing it out like this. You're just dividing the entire beginning equation with x plus 2, which is when you solve for x, you get negative 2. So what that ends up being is 12x cubed plus 29x squared plus 8x minus 4. So because that constant canceled out and all of these lost an x because we're dividing by x plus 2, each of these gets an x taken off of them. So that negative 4 that used to be in that 12x spot, that 12 used to be in that x spot, well, it turned into a negative 4 and it lost an x. So that negative 4 is going to become the next constant, which means all of them are going to lose an x, which means that what used to be 66x squared, once it's divided by our actual root, is going to turn into 8x. So, and so on and so forth. So that exponent of 4 turned into an exponent of 3. The exponent of 3 turned into an exponent of 2. So now our new equation that we have to use synthetic division on a second time to get a quadratic function is 12x cubed plus 29x squared plus 8x minus 4. Now to complete the second half of part B. So what we're going to do is we're going to take this cubic function that we have here, and we're going to use synthetic division on it a second time so that we can turn this cubic function into a quadratic. As I might have mentioned earlier, I've already done this problem on a separate piece of paper for the sake of the video. And so I know that we need to divide all of this one more time by negative 2. So if we put them all back in place again, like we did with synthetic division last time, so the 12 goes there, 29, the 8, and the negative 4, and we run negative 2 through it again, we find out that 12 drops down, multiplies to negative 2, it becomes negative 24. Add that to 29, you get 5. Multiply that by negative 2, you get 10. Add that to 8, you get negative 2. Negative 2 times negative 2 is positive 4, because negative times a negative is a positive. Add that to negative 4, and it cancels out. So now we have, oh, there's nothing there. Sorry. So what I meant was, what we just did up here was equivalent to dividing 12x cubed plus 29x squared plus 8x minus 4 by, so take all that and then divide it by x plus 2 again. And the reason that this is a negative 2 and this is a positive 2 is, again, because we get the negative 2 after taking this denominator here and setting it equal to 0 and then solving for x, which means that when you solve for x, the 2 will be flipped across, which means it'll change sign. It'll be flipped across the equation sign, which means it'll change signs. So that's why this is a negative 2 up here, but this is a positive 2 down here, is because this denominator hasn't been solved for x yet. And so what we do once we synthetically divide all that is these numbers down here, the 12, the 5, and the negative 2, are going to translate into 12x squared plus 5x minus 2. And now that it's in a quadratic function, we can move on to part C, which is factoring. So now we're at letter C, which tells us to use the quotient from part B to find the remaining roots. So we actually got 2 of our actual roots from part B because, remember, we used synthetic division twice. So we divided the initial equation, the beginning equation, by x plus 2, and we got the cubic equation. Then we took the cubic equation and we divided it, used synthetic division on it again, also by x plus 2, which gave us that quadratic. So what we're doing in part C is we're essentially taking that quadratic and, sorry, that's for a later time. We're taking that quadratic now and we're factoring that out. So we already have these two, which means if we factor these two out, if we set these two equal to 0 and then solve for x, we'll get our x-intercepts. But that's for a later letter. So what we're going to focus on right now is just this part right here, the quadratic function. And so what we're going to do is we're going to use basic factoring that we learned in previous math lessons by taking the a value and the c value. Remember, in quadratic functions, there's an a, b, and a c. And we are going to multiply a and c together to get 24. Well, now we got to factor out a and c, which means you got to find the factors of 24 that when they can be added together, one of them can, either of them or just one of them could be a positive or a negative. You have to make kind of the right mixture, so to speak, to get the b value. And in this case, when you factor out 24, you get 3 and 8 as one of the factor sets of 24. And if you notice, if you take 3 and if you turn it into a negative and you subtract 3 from 8, you get 5. And so what we're going to do here is we're going to actually split up that plus 5x into 8x minus 3x, so that we have 4 different terms that can be split in half along the equation, and then we can factor out those 2 different terms. So we're going to factor out 12x squared plus 8x, and we're going to divide that. We're going to take the like terms from this part, and we're going to bring it outside of the equation, and then we're going to find the like terms in here, and we're also going to bring that outside the equation. And when we do that, we get 4x. So the like terms for 12x squared and 8x is 4x, because 4x can go into 12x squared and 4x can go into 8x. But when you take the 4x out of this initial equation right here, you get 3x plus 2. And when you do that to the other side, you also get 3x plus 2 inside the parentheses, which is exactly what you want. You want these two to be the same. But in order to get this, because these have different signs, see? This is a positive, and both of these are negative. So what you had to do is you had to divide this, kind of, by -1. So you take that out of the parentheses, and you end up with 3x plus 2. Well, you can write this out, this bottom line here. You can write that out by saying 4x minus 1, because the 4x right here is on the outside, and the -1 is on the outside, so you combine those two, times 3x plus 2, because these are the same. So now we have our 4 roots, so to speak, our factors of the equation, which are 4x minus 1, 3x plus 2, x plus 2, and x plus 2. We got these in letter B. So that's how we get these. These two have already been found when we were doing the synthetic division in letter B. But these two have been found because of the factoring we did for the quadratic equation. Letter D tells us to use the leading term test to determine the graph's end behavior. So what the leading term test is you're going to take, sorry, it doesn't kind of fit, but there we go. If I slant it, it fits. So what we're going to do is, well, we're going to find our leading term in the initial equation. And what we're going to do is, so the leading term, that's the term that has the most exponents. So 12x to the fourth is our leading term, which means 12 is our leading coefficient, as we learned earlier, right, when we were finding out the possible rational roots. So the leading term test is a test for this number right here, this leading coefficient. If the leading coefficient is greater than 0, then the end behavior for when we graph this equation is going to have a rise to the right. As the graph is going right, it's going to go up on the graph. If the leading coefficient here is less than 0, if it was a -1, or if it was -2, any kind of negative number, then it would fall to the right. It would, as the graph would go right, it would gradually fall and go down. And so we're just writing that down on paper just to kind of verify. So the leading coefficient, the LC, is 12, which is greater than 0. And so the graph's end behavior will rise to the right. As the graph goes right, it will go up. So that's pretty much all we have to worry about as far as D is concerned. E is going to tell us to find the x-intercepts. So this is where we bring in those factors that we figured out during B and C. We have, ignore that multiplicity right there. And so what we're going to do is we have our one of the first terms that we found out when we were factoring out the whole equation was x plus 2. And of course, as I mentioned a bunch of times earlier, whenever you set x plus 2 equal to 0 and solve for x, you get x equals -2. So then you just do that for the second one, because the second real root, the second actual root that we got for the equation was the same thing as the first one. It was x plus 2, which when set to 0 and solved for x, you also get -2. So what these two are is, these two are a multiplicity. And the rule for multiplicity is when you have two x-intercepts that are equivalent to one another, when you graph it, they touch at the x-axis and then turn right around. So they technically still are x-intercepts, but if you have two x-intercepts that are equivalent to one another, they're the same, like the two that we had at the beginning, then they just touch the x-axis, either going up or going down, and then they turn right around and kind of go in the same direction where they came from as far as range is concerned. So we're going to go on down the line. One of the other factors we had was 4x minus 1. When you set that to 0 and solve for x, you get x equals 1/4. So 1/4, 0, is going to be one of the coordinates of our x-intercepts, as well as -2/3. So our coordinates for our x-intercepts, I'm going to write them on the bottom here, is going to be, and you write them like an ordered pair, it's going to be -2, 0, another -2, 0, 1/4, 0, and -2/3, 0. So those are our coordinates for our x-intercepts. For letter F, we need to find the y-intercept, and this function was actually really kind to us in providing a constant. So when a graph has a constant, the y-intercept will always be at that constant because there's no x value. The x in here is 0. And so if it didn't have a constant, then what you would do is you would take the entire equation, take all the x's and put them at 0, and then you would solve. And what that does is, say that this 8 was taken out, and say that all that we have is just 12x to the fourth plus 53x cubed plus 66x squared plus 12x. Well, if you set all these x's to 0 and then solved, then 0 times itself 4 times would be nothing. So it would still be 0. Times 12, that would still be 0. So in this section, we'd have a 0. X times itself 3 times is still 0. Times 53 is still 0. And if you see where I'm getting at, if there's no constant, the y-intercept is going to be 0. Because if all the x values are then changed to 0 and then solved for, the entire equation is going to come out to 0. So our x-intercept, because of the constant, so the constant was -8, which means that our y-intercept is at 0, -8. And the next step for g is we're going to graph it. So this is the graphed equation. The units, I made 2 of these little, on the graph paper, the little squares on them, I made the space of 2 of the units equivalent to 1 just because we were working with fractions like 2/3 and 1/4. And so as a result, I wanted to zoom in on the scope of the graph a little bit more so that we could see those values rather than just having a dot somewhere. So that the placement of the x-intercepts and the y-intercepts could be a little bit more precise. Down here, you'll see the y-intercept that we have. There was a really big, a really steep fall and then a climb back up to get to those x-intercepts because those are actually pretty close to each other. But I'm going to actually take the camera for a second and I'm going to bring it really close. And if you can see it, it's not... The one thing I didn't do to the x-intercept when I brought this line down is with that x-intercept, I didn't bring it down and then immediately bring it back up. Because what that would be is that would be creating 2 straight lines that connect there. And what that's for is that's for an absolute value function. And that's not what we're doing. And so what I did was I did a slight curve, it's barely visible, and then slowly brought that line up until it made it all the way to 1/4, which is halfway in between right here and here. So I'm going to try to set the camera back. And now what we're going to do is we are going to list all the major parts of the graph. So down here, obviously, because I was talking about it, is going to be the y-intercept. And that's just kind of the reference. Now, even though it was an equation where 4 was the exponent, was the highest exponent in the x, we still technically have 4 x-intercepts. But if you remember the multiplicity we talked about earlier when we were finding the x-intercepts, the third and fourth ones are actually on the same point, which is why it doesn't cross over the x-axis. It just kind of bends and goes back the way it came. And we know that it goes up because the exponent, the largest exponent in the equation, was an even number, which means it's going to follow the same direction as the end behavior of the graph. If it was a cubic function, then we wouldn't have a 4th x-intercept, which means this wouldn't turn around and this would go straight through the x-axis and it would continue on down in this area. But since we do have 4 and 2 of those are the same point, we have our first x-intercept, our second x-intercept, and our third and fourth. And the 2 right here will actually go through the x-axis because there was only 1 of each. And so I'm just going to write x-intercept. I'm abbreviating so that I don't write into the y-intercept, the y-axis rather. And then I'm just going to go ahead and just kind of give them broad points so that they're just kind of generally labeled. And that is how we graph our function.